we are our n tends to infinity. That is, we consider in each Rn we consider a lattice, and then we consider a family of such lattices with group n. Then the parameter we are interested in is called the lambda, which is minus 1 over the dimension. Yes, so this lambda, which I define as 1 over n binary log of the density of the lattice, asymptotically is expressed as some constant. Let me write it this way, minus log of the minimum distance over the square root of the dimension, and plus 1 over n logarithm of the determinant of the co-volume. So, so last time we, let me recall that if lambda is non-zero, then the lattice is the family of lattices is called asymptotically good. The reason for it is that if you construct some lattices or take them from literature and you look at how they behave at the limit, how they behave in asymptotics. See, if you may take an root lattices or dn root lattices or something else, then the typical behavior is not 2 to the power minus constant times n, which we wish it to be, but rather n to the power minus n, which is much worse. So, of course, you can get another constants here, and you can maybe even do better than this in a way, but as soon as you achieve this kind of behavior, you see that it's asymptotically good. Now the construction, which you...
Just a question. The n to the n, does this come from factorials at some point?
Yes, right you are, yes. It's just, first of all, the standard square lattice behaves like that. Then if you take the root lattices, it behaves better, but it is in the constant. And to get this, you have either to use a randomizing argument, because most part of lattices behaves like this. But you are unable to produce a direct construction. And when we started this business some 25 years ago, new family, explicitly constructed family with such behavior was known. So at first there were very difficult constructions that constructed non-lattice sphere packings by a direct construction, but ugly one, like this. And then I found these easy constructions. So last time we had K, OK in it, and then we embedded it into the product over S infinity of R's and C's. Now this time we'll do something similar. That is, I'll take the multiplicative group of the field. I have a map. So which map I take? So in the number field case, I take the logarithm of meaning that if I have an A here, then it is mapped to the string log absolute value A V, if V is real. So this is real. And log A V squared if it is complex. It's just the square root of 2 you saw in the additive construction. So here you have to square. So again, you choose all infinite product over S infinity, but this time it's just a product of real numbers because the value of the logarithm map is a real number. So this is R to the S plus T. As the number of real embeddings, T the number of complex of pairs of complex embeddings. That's in the number field case. In the function field case, you do the same, but this time the natural analog of the logarithm is just the divisor. So an element here is a function. You take its divisor, but I'll leave it. Of course, this divisor, you see, you want to get a finite product here. Therefore, what you do in the function field case, here you just know you take only the infinite places, and you know that. I'm wrong, by the way. Let me say it differently, that here I take an S that contains all infinite places but need not coincide with it. And then here I get the number of finite places I have added to it. I can do this as well. But for simplicity, you may consider that S equals S infinity. So here we have only finite places, and I have to choose a finite number out of those. So for the function field case, I have my curve X, which corresponds to the field K, and I have take P, which I would like to be contained in the set of FQ points. That is, I take places of degree 1. Again, you can avoid it, but the estimates will be slightly different. And then I take, instead of taking this divisor map for anything, what I do is that here, instead of inside of K infinity, I take those functions whose poles and zeros are contained in P. So these are units with respect to P. So outside of P, there are neither pole nor a zero. And then here I take the divisors, only the part of the divisor that is inside P. And then here it goes to Z to the number of places in P. And if I take it here, then it's a proper divisor map. So if I restrict it to functions whose poles and zeros do lie in this set. And now, of course, what is, well, so here I won't bother anymore with the finite places, and I'll just return to what I had here before. And then you see that the determinant of this lattice, the lattice is the image, but, well, sorry. Of course, this is not discrete. So to make it discrete, I take the units here. just as I took the integers there. Then the image is discrete. We know that it's nearly a full rank in the sense that, of course, it lies in the image. Let me write it like this, that the image lies, which is the lattice, lies inside the hyperplane, the sum of coordinates equals 0. That's because I consider the units, and the norm of a unit is 1, and therefore its logarithm is 0. And in the function field case, again, this is a principal divisor. The divisor map gives you a principal divisor. The degree of the principal divisor is 0. So here again, I get L, which lies in the hyperplane given by the sum of coordinates equals 0. So I know the rank. Here the rank is S plus T minus 1. Here it is the number of chosen places minus 1. Now about the covolume. The covolume in the function field case is just the regulator. It's the definition of the regulator. The covolume in the function field case is slightly tricky. It will be just slightly tricky as well if you take not only infinite places here. But that's a good exercise to understand what the... it will be the regulator times the some part of the number of classes. Because if you add some finite places, they generate a subgroup in the group of classes, and the number of elements in that subgroup multiplies the regulator. And in this case, let me argue like this. So I repeat the construction. I have the OK star, OP star, sorry, and I have the divisor map. So I come into the set of the principal divisors based with support in P. Now, what is the covolume? The covolume should be calculated inside this plane, of course. So the plane is skew. That gives you something like square root of n that I'll ignore at the moment. But then then what is the covolume? It's you need the volume of R to the power, well, let me call it n. Let n be the number of places, of chosen places. Yes, so I should take Rn. What is Rn? Sorry, not Rn, but Z. How to put it? Let me do it like this. So my lattice L lies inside the hyperplane H, inside Z to the power n minus 1, to the power n, sorry, and this inside R to the power n. So I have to calculate the covolume here, but not in this case, but there is an HR here, this, the sum of coordinates equals 0. So how to do that? First of all, I take this, the covolume of this space over H. So I have to calculate covolume of this HR over H. That's one thing. And then the index of L inside H. And so what is H? H is the set of of all devices of degree 0 supported at P. Therefore, what I have to calculate is the factor group of devices of degree 0 supported at P over the principal devices supported at P. And this is definitely smaller than all devices of degree 0 over all devices, all principal devices. So therefore, the index of H over L is less than or equal to the number of classes of my field K.
Isn't it just, so say the S part of the class group?
Yes, it's the S part of the class group. You can say that. So,
HKS.
Yes, it equals HKS. You are right, and this is HK P. P and P is the S in the function field case, yes, and which divides and therefore is smaller than HK. So at least you have an upper bound for that. Now you need a lower bound for the minimum distance. So how to obtain the lower part for the minimum distance? So you
don't calculate the co-volume of HR mod RH?
Yes, I did, because this co-volume, well, if you want, I think it's square root of n, but looks like that. But if you want me to be precise, I can look it up.
No,
you believe me.
You went on, so it was not clear whether you
yes.
calculate.
No. This is easy. This is easy because of that. I didn't write it down. So therefore, the co-volume is square root of n times this class group, the number of classes. Now, how to calculate the minimum distance? As for the number field case, I was asked today whether I'll tell it to you today in detail. So in the number field case, I won't, because it's pretty tricky. And moreover, I do not know how to do it. What I do know is, so in the number field case, so this is, I have to estimate d of L from below. So in the number field case, I can do that only if I know that one of the places split completely. So I have a condition. See, for example, suppose that all fields in your tower are totally real. That is, that the real point splits completely. Or instead of that, you may say that there exists a place that splits completely. Well, in this case, we have an estimate. I'll give you the idea of what the estimate is in the totally real case. In the totally real case, we have just used, it's Rosenblum and myself who treated these multiplicative lattices. And there we used a result of Schinkel that says that just a minute. Yes, and now maybe I should mention that what I'm interested in I have to minimize, to estimate from below h of f, that is the sum over v, the absolute value of logarithms of the norm of f at the place v. This is a height function. So this is a height function known in number theory.
What is f?
F is an element of K, or F is an element of O star S, S infinity. So, yes, I called it A before. Let me write it A.
This is, I mean, you need to bound the generators for the height of generators for the
yes, yes, to estimate it.
Regular, you need to an estimate for the regulator.
Right, right. But this is slightly different because here A is just an element here. And of course, you can take the generators, they are shorter than everything else, usually. But in that case, you have, but not always. So you are looking for a shortest vector. And, but anyway, for a given A, you have to estimate this from below.
But can't you do that by Minkowski? I mean, it's first success minimum.
Oh, yes, yes, you can. You can, but I do not know how to get good estimates from that. We need a lower bound
yes,
here.
But you need to do estimate the volume of the lattice.
No, volume of the lattice we have estimated. Here we estimate the minimum distance of the lattice, the shortest vector.
Don't you, if you have the volume of the lattice, don't you have a lower bound for this success?
Yes, but that's definitely bad. We do have, but it should be bad because suppose that you have any lattice. Of course, you can get some bound for the minimal distance, but this bound, worse than that, this bound is based on the fact that the density of the lattice cannot be greater than 1. And your goal is to show that it is much better. So that's, in that case, you already used the density argument. So you know that the density never exceeds 1. And of course, what you get is very bad. So you need a good estimate for this. For a totally real field, there is an estimate by Schinkel, which is K over Q times logarithm of 1 plus square root of 5 over 2. But here, in fact, if you listen a bit further, you'll understand why in these two cases we can give an estimate. Because there are two ways to give an estimate for in the function field case. The function field case I'll treat in more detail. But here the only thing I may want to be proud of is that this is already enough to say that the sequence, that if you take an unramified tower of totally real fields, then the lattices you get, the families, are asymptotically good. The constant is not very good, it's 6 point something, I think, but at least they are asymptotically good. They do behave like 2, the density does behave like 2 to the power minus constant times n. Now, how to do this in the function field case? In the function field case, I have a function f, with the property that its divisor lies inside P. That is, that it's the sum of AI Pi for Pi in P. So I'm interested in the minimum distance. That is in the square root of the sum of AI's squared. Now I know that these coefficients are integers. Since they are integers, this is greater than or equal to the square root of the sum of the absolute values of AI's. So that's all with that chalk. Now, I know that the degree of this principal divisor is 0. Therefore, the sum of positive AI's equals the sum of negative AI's. That's square root of 2 times the sum of AI's, where AI is positive. And what does this mean in geometric terms? So you have your curve x. You have your function your function f that maps it onto a projective line. You have a 0 point here, and AI's are multiplicities of what is lying over 0. So it's this, the pre-image of 0 divisor. This means that what you have to estimate the minimum of all this, let me write it here, that the minimum of all this, is just what we call the diagonality of the curve. That is the lowest possible degree with which we can map it onto a line. So for a hyperelliptic curve, it's 2, for a trigonal curve, it's 3, and so on. So you need the degree, the smallest degree of a function on the curve, in fact. And now I have to bound this value from below. There are 2 ways to do it. So one way is that just remember that we are over a finite field. Since we are over a finite field, the number of places of degree 1, the number of FQ points here, is Q plus 1. The number of FQ points here is the number of FQ points. And each FQ point above is mapped onto an FQ point below. Therefore, this thing here is greater than or equal to Q plus 1 times the degree of this function. And this is the degree of f. Square root of 2 times the degree of function f.
Sorry, perhaps the equality is in the...
Yes, the other way around. The other way around. Yes, and this gives you, thank you, this gives you the estimate of the degree. Therefore, I can write here square root of 2 times the number of places of degree 1 on x over Q plus 1. And if, which we usually do, I take P just to be equal to x of fq, then this is square root of 2 times n over Q plus 1. So that's what I promised to you. So in this case, the estimate is easy. And what is very important, that if you look at the answer, this is a constant times square root of n. Small n equals large n plus 1. That is asymptotically, that's the same. Therefore, this term here is a constant. And this term here is a constant as well, provided that you take a tau of unramified extensions. For an unramified extension, the nth root of the discriminant doesn't grow. Yes, and the nth here you have a regulator. Yes, it's a bit trickier. So now you have a regulator here. Maybe a regulator multiplied by some part of the class group. In any case, it's less than the regulator times the class number. And regulator times the class number is given to you by the Brouwer-Ziegel theorem. If you look at the Brouwer-Ziegel theorem, you see that this is a constant as well if the discriminant behaves well. And the discriminant behaves best of all if the extension is unramified. So you use the Brouwer-Ziegel here and the fact that you take unramified taus. Now, I have cheated, grossly cheated. Where? Do you see it? No, that's very good. So that was totally false, what I was saying here. But it was on purpose. Now I'm passing to the last part of my talk. That is why this was false and what is true. There will be no more lattices. Well, maybe because of that I erase all this. Yes, I can erase all this. Let me recall what the Brouwer-Ziegel theorem is. So now we're speaking about the Brouwer-Ziegel theorem. You have a family of fields, K1, and so on, Kn. Now, for simplicity, this is not required, of course, in the Brouwer-Ziegel theorem. But I would like you to think that they are embedded one in the other, that this is a tower. In fact, Brouwer-Ziegel doesn't require it, neither I require it. I require something much weaker, but I'll tell you what. Now, the Brouwer-Ziegel theorem tells us I'll write it out and then I'll pick up what I have written for you. So it tells us that the logarithm of HR over the square root of the discriminant of the absolute value of the discriminant of the field in the limit tends to 1. When this is true, there are two types of conditions. So the first one I'll call technical conditions. And the second one I'll call important conditions. So the technical condition is that we know that something is true, but we are unable to prove it. So the technical condition should be either the generalized Riemann hypothesis or the Artin conjecture or normality of the fields in this sequence, or as Alexei Zhikin, who is here, proved, almost normality, which is that it's normal. A field is, suppose that you have a field, then you have Q below, and it is filtered by subfields such that each pair is normal one over the other. Then we call it almost normal. So almost normality here is enough. But this is technical because we do believe, at least I do believe in GRH, and therefore, well, in fact, everyone in algebraic number theory believes in GRH. In analytic number theory, that's less.
Otherwise, they are jobless. So
absolutely. Now, what is an important condition? An important condition is that the square root of this discriminant, which further on I'll call the genus, because it's a good analog of the genus of the curve, or of the genus plus one maybe. So let me say that I call square root of the absolute value of this discriminant the genus in the number field case. So what is important that the genus of K over the degree of K over Q tends to infinity. Usually the people write it the other way around, that the degree over the genus tends to 0. And this is not true for unramified towers. For an unramified tower, this is a constant. Well, I write stupid things here and you don't correct me. I'm sorry. This time it was not on purpose. I meant the ratio of the logarithms here, and I meant the logarithm here as well. Yes, in the function field case, you have the same Brauer-Siegel statement. Of course, you have no technical conditions, and in the function field case, you may wonder what is H times R. So you do not know what R is, but what you do know that this product is just the number of points of degree 1 on the Jacobian. So this product is well correct, is well defined. You have a genus here. You have exactly the same statement under exactly the same condition, but here instead of the degree of the field, you should have something else. I'll tell you which. I'll tell you what. So now, what I'm interested in. Suppose that I believe or almost believe in all the technical conditions here. What shall I do if this is not true? Is the Brauer-Siegel true or false in that case? The answer is that it is false, but that a slight generalization of it saves the situation, and you can, and that we do know the result. So I need some definitions. So suppose I have a global field K. It may be function or a function field or a number field, and then I have the following parameter of it. So let alpha be an element of the following set. R, C, it's an index, so R, C, or Q, where Q is a prime power. Well, in the function field case, there is no R, no C, and all the prime powers will be the, of course that's bad for the audience, but I need to do it. So in the function field case from now on will be over function field case. We won't be over FQ because Q will be a prime power, but it will be a curve over FR. So, and in the function field case, we should consider only those Q's that are powers of R. And then let capital phi alpha of K be the number of places. Well, here I do not know how to say it. I'll write places with residue field FQ. And of course, if alpha is R and C, this means real places and complex places. So each place of your field belongs to one of the elements alpha. And so the number of such places, I call it capital phi alpha of K. And, well, is it correct that you do not see what I write below? Should I write higher? I'll try to. Now, this I may erase. Now I'm not in a field, but in a tower of fields, Ki, or in a family of fields, any family. What I would presume about this family is that G of Ki tends to infinity. That's not too much, but just in the number field case, if you have an infinite family of different fields, it's always like that. In the function field case, you should avoid the situation when an elliptic curve is covered by another elliptic curve, another elliptic curve. But again, over a finite field, you have only a finite number of fields with a given genus, so that's no restriction. So you have this Ki's, the family, and now I define small phi alpha as the capital phi, as the limit of the capital phi alpha of Ki over the genus of Ki. And these are very important parameters of the field. Now this limit need not exist. It's not a real problem because what I just recall several elementary results that you will prove yourselves, which is that if this is not just a sequence but a tower, then these limits do exist. If the limit doesn't exist, in each family there exists a subfamily for which the limit exists. That's true as well. From now on, I'll consider what we call asymptotically exact families, that is, the families for which all phi alphas do exist. And if you need to to work with an arbitrary family, you just use the fact that inside you can find families with the corresponding to one or other limit point. So that's no problem. Now I'll write out the true Brouwer-Siegel theorem, in this case, proved by Ledwitz and myself, the correct one. Here it is, that I'm interested in this limit. So let me write here a limit, and let me call it Brouwer-Siegel of, well, I'll write it as a script case. The script k is the family, and the limit is over the elements of this family. So these are ki's, you take a limit and you get this value. Here is the theorem, which is that this Brouwer-Siegel of k equals 1, just as in the classical case, plus something else. Something else is the sum of over q's, q a prime power, phi q log q minus 1 minus phi r log 2 and minus phi c log 2 pi. And so what is important for me, there are two things. One thing is that we can write it out. Another thing, that's number 0. Number 1 is that this is a linear expression in phi's, which is very important. And the second thing, which is yet to be proved, is that it is bound from above. Now, what happens, yes, here there is just one thing to be remembered, because I write the logarithm. And if I write 1 here, then I should define the base of this logarithm. And in this theory, the base of the logarithm is just e if we are in the number field case, and r if we are in the function field case. So let me write it down. Log equals just the natural Neperian logarithm in the number field case. And log r in the function field case. In the function field case, what I should say that I do not allow, in the tower, I do not allow the constant field to grow. That is, that these are fields corresponding to curves over a given field fr. And so this is the r function field case over fr. And of course, in the function field case, you do not have these two terms, and all q's are powers of r here. And there is, now what we know about phi's. We know that they are non-negative. Phi alpha is non-negative. Then in the number field case, there is an extra condition, which is that the sum of m phi p to the m for any prime p, so m from 1 to infinity. This is the, so to say, the number of places over p, and it can't exceed the degree, so it's less than or equal to phi r plus 2 times phi c. So this we know as well. and what is important, we have what we call a basic inequality. So it is known in different forms, provided whether you believe or not in the generalized Riemann hypothesis. I'll write to you the easiest one, which is under the Riemann hypothesis. In the number field case, yes. In the function field case, it's true as well. Yeah. So the sum over q phi q log q over square root of q minus 1 plus phi r multiplied by a constant which is log log square root of 8 times pi plus pi over 4 plus gamma over 2. You should add to this phi c times another constant which is log 8 pi plus gamma. Gamma is the Euler constant, the Euler constant, I mean. The Euler constant. So all this is at most 1. Now let me look at this thing.
So in the second case,
sum over all prime powers.
Prime powers.
Yes. So if you forget this first term here, what you get, the inequality for infinite places, will be the Adlichka-Serre inequalities under the Riemann hypothesis. If in the function field case, these two terms do not exist, and this term, q is a power of r, say r to the m. So in the function field case, what you get is the sum of phi r to the m times m or r to the m over 2 minus 1 is at most 1. And here the sum is over m from 1 to infinity. And if you take just the first term here, that's the Drinfeld-Ledus theorem that tells you that asymptotically the number of points over the genus is at most square root of r minus 1. So this is a generalized Drinfeld-Ledus, and this is a generalized Adlichka-Serre, whichever you prefer. And so now we have some linear conditions on phis, and we have a linear function in phis, and then so we can use linear programming technique to answer the question that is natural to ask: what is the minimum and maximum of this value? So so Brouwer-Siegel is 1 plus something. So is it far from 1 or close to 1? So under the Riemann hypothesis, it happens to be pretty close to 1. So in the number field case, let me see. Yes, it's in between. Let me write it maybe on this part of the board. So the Brouwer-Siegel under the generalized Riemann hypothesis is between 0.5165 and 1.0938. And using some special, constructing some special Goldschaft towers, you can prove that it does happen that Brouwer-Siegel is smaller than 1, and it does happen that Brouwer-Siegel is greater than 1. So in the unramified case, or in the case that resembles an unramified one, because see, if you take towers of modular curves, the tower is not unramified, but the ramification is small with respect to the degree. And in the limit, it just behaves, the discriminant behaves as if it were unramified. And so in all those cases, you actually do not hope to get 1, but you hope to get something which is close to 1. In the function field case, the Brouwer-Siegel quantity, I'll write it in other terms that are less precise, but maybe more clear. What is the number of points on the Jacobian of the curve over FR? So it's roughly speaking, roughly means exactly that you should take the logarithm, divide by the genus, and so on. But roughly speaking, it's q to the power the genus times q means r, sorry, r to the power the genus, r over r minus 1 to the power of the, well, one thing to be introduced. What is this? What are these phi's for a curve? So the capital phi r to the m is in fact the number of the number of places of degree m which I call, say, Bm. Of course, you have that Nm. If you consider your curve over an extension of degree n, the number of points is the sum over d dividing m dBd. And so here I'll have B1, the number of, which equals to N1, the number of FQ points. Now, then I should multiply it by r square minus 1 power B2, and so on. So this is the main term, and these are the corrective terms that are responsible for the fact that the curve may have many places of lower degrees. So, and to make this statement true, you have, as I have said, to consider the Brouwer-Siegel quantity and take, and then you'll get that Brouwer-Siegel of k just is 1 plus the infinite sum over m of mbm over r m over 2 minus 1. No, that's wrong. Definitely wrong. So here you should get the sum of phi r to the m. I have used the long formula. Log r to the m, r to the m minus 1. Sorry. And this phi r to the m is the limit of Bm over the genus. Now in the so I have chosen this topic not only because it is very much related to sphere packings, but also because it's a good illustration of what questions arise when you study codes on sphere packings. So this question was never asked before. So I know that Keith Conrad, roughly speaking, at the time when we are already working on it, he was the first to ask Maser whether it's known or not what is the Brouwer-Ziegel in the unramified case. Can it be different from one or not? So it's funny because the question could have been asked in 1940s, and people were just not looking in that direction. Now maybe I'll go back to sphere packings for a while and tell you the second way. I promised to tell you the second way to estimate the gonality. And this will give a different construction. So the second way to estimate the gonality is, so I recall that we had OP star and that we mapped it to, by the divisor map or the logarithm map, well, let me be in the function field case now, by the divisor map to z to the n. Now what I'm going to do is, just remembering about the coding construction when you needed a divisor to get an embedding, well, I think I have 2 minutes, don't I? I started later. Okay. Well, I'll finish the sentence. Yes. Let us fix a divisor, an effective divisor. And inside this, consider a subset, a subgroup of PD that consists of functions that are congruent to 1 modulo this divisor D. Then, of course, you have another argument for the gonality. That is that you have to estimate the degree of f. Instead, the degree of f equals the degree of f minus 1. And the degree of f minus 1 cannot be smaller than the degree of D. So the degree of f is greater than or equal to the degree of this divisor. And that's, roughly speaking, what you should use in the number field case, as far as I understand. So I may stop here. Thank you.
Any questions, comments, remarks?
Yeah.
I mean, how far is this effective? I mean, you want to construct a curve which has certain properties, but this seems more asymptotic.
Absolutely. Absolutely.
So can you do this effective? So at some point of that you can get an effective bound such that the curve has the property.
Yes. Thank you for the question. The answer is I can't, but they can. So Philippe Lebac and Alexei worked on it, especially Philippe. And Philippe has, what we did, we passed to the limit very fast so as to make the things easier. What Philippe did, he worked the error terms, so to say, on each step. And because of that, he has results on finite level, estimates on finite level, that give you this as a limit. So this can be done. But of course, the formulae are less beautiful. They are very complicated.
But it seems that there is always the generalized Riemann hypothesis is coming in.
Oh, yes and no, because you see, in fact, in the number field case, if you do not presume the generalized Riemann hypothesis, then you still have estimates, but see there was an inequality here I used. So the inequality is no more provable, but you change the coefficients. You take worse coefficients, and then it is true as well. So some inequality replaces it in an unconditional case. The same thing here, that of course you do not get these bounds, but instead of 1.09 you get 1.21 or something like that. So you still get the results. The only thing that is ruined is something I wasn't speaking about, maybe Alexei will, is the description of the zeros of zeta function. So this is, very, to my understanding, very elegant, and it is ruined completely unless you believe in the generalized Riemann hypothesis. But this theory is preserved, but it becomes worse and more difficult to prove.
Tried applying it to, what happens if you plug in a sequence of fields where you somehow control the regulator, for example, cyclotomic fields?
Well, for cyclotomic fields, you have a behavior of the density n to the power minus constant times n. So it is bad, and you understand the reason, I think, because the discriminant of a cyclotomic field doesn't behave as constant to the power of the degree. But it behaves as constant to the power degree times log degree.
The class number is divided by the class number, so that may work for you, right? To get the regulator.
Yes, maybe, but of course, what I estimate is always the class number times the regulator. If you are able to work with the regulator itself, you may get something much better.
If you have precise knowledge on the regulator, you can bypass Siegel-Brouwer.
Right. But as yet we worked it the other way around. That is, we ameliorated on some estimates for the regulator by Friedman using this theory and not the other way around. So,
but do you always bound the class number from below by 1, or do you also employ some?
No. We do employ all this theory of the last part of the talk. Yes, by 1 that would be uninteresting.
Any more questions? If not, so then let's thank the speaker again for an interesting series of talks.
Thank you. The pleasure is mine.